Let's talk about using color as an nth dimension when it comes to working with your students, specifically with mathematics. Let's take a look at an example here. This is a nice bowl of fruit, right? Well, what if you in particularly take it and change it to completely black and white? Can you see the different colors? Well, no, not anymore. That's because your brain is actually filling in. Your brain can't tell that there is a difference between here if you didn't see that color originally. Now you can see that there's obviously a difference in color there, and there's a difference in shape, but those things would not exist without color specifically. The natural world is designed specifically to have color all around, and you can teach your students how the relationships between numbers and the relationships between colors are similar and can be interchanged. So let's take a look at this in particular example. You'll notice that I have an A, a B, and a C. All three of these things are all connected by color. So the 7, the 6, and the 5 over here, you know automatically go to the A. Yes, that's right. You didn't have to actually point an arrow to them. You didn't have to explain to the student that this 7 probably goes in the A slot. They can just realize that because this is an extra dimension on top of your normal workspace. You can add it as an extra piece of information that doesn't directly interfere or change out the results of your answer. You could have just easily circled every single one of these and connected them over and changed the whole thing to black and white. But that doesn't look as pretty, and that doesn't help directly relate everything all at once. Changing everything to color gives you a lot more information and acts as a second dimension over the entire surface. You can also use color as a dimension to connect different parts of different shapes. For example, I can connect that this angle over here between the blue and the red is the same as this angle over here. I can know that the blue and the blue and the blue lines are all going to be the same because they're all blue. In geometry, we typically use these line segments, 1, 2, or 3 lines, to talk about the different distances and show that each of those are congruent. But you can use color to show the same thing in a cleaner format. In addition, you can also show relationships between things without actually needing them. So say, for example, I have this purple angle over here, and I have a gray angle over here. If I wanted to show that both of those are equal to 180 degrees, I can actually put a line down here and show students that there's a connection between this purple angle and this gray angle that line up to create a straight line. Once again, I didn't have to use any numbers, and this creates more of a general form. This is less confusing to students than simply putting like a theta or an alpha over here. Instead, I can actually just put their colors and respective information, and it makes a lot more sense for most students. So you can use color as an extra dimension. So what does that actually mean for category-wise? Because does one color outrank the next color? Well, for my in particular classroom, I have blue as 1, 2 as red, 3 as green, 4 as orange, 5 as yellow, which I'm going to put in here as black because yellow doesn't show up very well. I have 6 as pink. I have 7 as purple. I have 8 as gray, and I have 9 as brown. And then 10 is actually considered white or black, depending on what I use. Or you could also look at that as 0. So if I color code my classroom, I can actually use it with this scenario. In my classroom, all of my tables each have their own color associated with that in particular order. Some people will have colors in different orders, and that's all right. Color doesn't actually need to have an order, but you can artificially add it into the system. Now, why do I say it's a nth dimension? Well, if you look at an XY axis, you can immediately tell that this point over here would be at -1 and positive, we'll call this positive 3 for simplicity. So this is -1, positive 3. So if I want to put that in coordinate points, I can put that as -1, positive 3. This point over here is completely independent of this point over here. It can always be -1, but it can be any value of the other thing. In the same way, color can be used as an extra dimension on things. This over here can be any shape, but it can also be any color. Color is not required for specific dimensions unless you specifically tell somebody that. So later on, you'll see an example that I use in my own classroom that requires you to use specific colors to create a scenario that helps the student understand information better. But for right now, know that any color can be used for any shape or any object. But this doesn't actually quite fit with anything that we can really categorize in a lot of ways. Colors fill a specific gap. So there's a difference between qualitative and quantitative variables in statistics. So this is part of my statistics class that I wrote. And you can see that qualitative variables talk about qualities or items' names, and quantitative variables talk about quantities or the amount of something. So numbers versus names. In the quality section, you'll notice that there are two levels. There's something first called a nominal level, and then there's something called a ordinal level. Colors fit nicely in between. So this is the ordinal level, and this is the nominal level. Colors fit right in between here. Why do colors fit in between there? Well, because they don't necessarily fit in either category, but they sometimes fit in both, and well, let's explain. So let's first qualify what a nominal system would be. A name would be a nominal system. So a car or a bicycle, let's create a little bicycle over here. And we'll create a little bell. There we go. All right, that's my bicycle. Now you'll notice that's called a bike, and this is called a car. Now, while you could argue that the car can run faster, they're essentially the same thing when it comes to names. One does not outrank the other. A bicycle is not any better than a car, and a car is not any better than a bicycle when it comes to advantages and disadvantages. Well, you could say a car runs faster. Yeah, well, a car also requires gasoline. A bicycle can be done entirely without gasoline. A bicycle can be ridden entirely without gasoline. So you can see how the name is nominal. There's no ranking system. Or for example, if I get injured in an accident and I break a leg, an arm, or my hand, those are just different types of injuries. A leg injury isn't any more different than an arm injury. I mean, they're both different injuries, but they're not any better or worse than the other. This name is nominal. Ordinal means that things have order, but they cannot be added together. So you can't get you can't get a B on a paper and get another C on another paper and add them together to get an A+. That's not how grading systems work. There's still a clear order where the A is clearly better than the B, and the B is clearly better than the C. However, you can't divide an A up into a B and a C when it comes to grading. Another example where this would be useful would be when it comes to musical notes. Musical notes, in particular, are ordinal because they are clearly higher or lower than one another. However, one is not necessarily better than the other, and you can't add two notes together to get a note that's higher. So you can't add a C and a D together to get a F, for example. That's not how the system works, and that would be considered ordinal. Likewise, you can't eat at 3 one-star restaurants and get the experience of a 3-star restaurant. That's how ordinal works, where there's clearly an order between them, but there isn't necessarily a connection point between them. Well, colors fall in an interesting category in this case. Colors fall in between these two categories. They, in some ways, can be ordinal if they want to be, but they don't necessarily have to be ordinal. They are clearly nominal, but they can also be mixed together and have operations on them similar to interval notation. So this is the reason why I classify colors as a separate dimension, similar to quality and similar to quantity, but yet not falling really into any of these categories. So what can you do with colors? Well, there's a couple things. First off, I always like to teach students that letters and variables are maps to my equation. Every single thing can tell you something about that equation and what you're supposed to go to or put in that place. So just like Dora the Explorer, we need the map, the map, the map. So you can look at an example like this. ax squared plus bx plus c is equal to 0. This is a great example. I can immediately put the number 5 down, and you know automatically where it goes. I can put the number b down, and you can see that b still stays the same. I could put the note 7, and it could still work. These things are connected. I could put the 7 over here. You still know it's connected. It does not necessarily need a direct line of sight, or it does not need a direct association or anything to indicate besides the color. Thus, this does categorize as a second dimension because one is completely independent of the other. This can be used to your great advantage when it comes to steps in math. So here's a great example when it comes to division. Let's say that I want to take 68 and I want to divide it by 4. First thing I'm going to do is I'm going to take the 4 and see how many times it can go into 6. It can go in there one time. So I'm going to put 1 times 4 gives me 4. 6 minus 4 is going to give me 2. That's all done within that first step. The next step that I'm going to do, I'm going to color in a different color. So I'm going to drop down this 8. And 4 can go into 28 how many times? Well, it can go into 28 7 times. So 7 times 4 is 28. Do the division or subtraction, and you are done. If students are still confused by this section, color it in a different color. Make it so your students are fully understanding what each steps actually do. I could color this over here in a different color. That way it's a little bit easier for your students to understand. Whatever works for you and your students, but you can use color as an advantage to clearly track information later. This can be done with numbers over here, and it can also be done with multiplication if you need to. But the biggest place that I've seen it used is in foiling. So, for example, this is the first, this is the outer, this is the inner, and this is the last. Notice each one has their own color. So the first one over here is going to be x squared. I've put that in blue. The second one over here is going to be 4x. The next one over here is going to be 3x. And the last one over here is going to be 3 times 4, which is 12. After this, you can combine things together. Show this is 7x. And if you want to, you can also keep colors in for specific things and remove them as needed. And voila. We have ourselves a system that is nicely solved. And this is a great example on how you can use colors to show association from things. Colors can also show association and connections between things that you don't realize until after